So yes, so in here in the multi-class classification problem, we do not have an imported data set, and we use the make classification method from the scikit-learn datasets to generate uh, a, a sample consisting of 3,000 observations with number of features equal to 2, number of informative features equal to 2, and we have some number clusters per class parameter in here, and we have class separations which is equal to 3, and we have number of classes equal to 3. So we have 0 and 2 as our class labels in our response variables, and the flip y is the if you remember, a flip is the percentage of the values while we plotted this sample taking the x1 feature as the x coordinates and the x2 features as our y coordinates, and when we plotted, we saw some percentage of the data points near the other class data points than itself, than the one that it corresponds. So our x has a shape of 3,000 over 2, so we have 3,000 rows and 2 features, and y is also contains 3,000 observations, and the general idea in here is pretty the same. We use the train test split to perform the k-fold cross-validation to estimate the optimal parameter of c in here. We see that for each c value in our list, the average cross-validation score is the same. So we can say that regularization in here has no effect on the performance of our model. So all our beta parameters in the model are important, and they're never equal to 0. And despite the fact that it has no impact on the performance of the logistic regression, we can just, for example, eliminate this from here, because in here this doesn't help, and will provide with and without C and penalty the same results. We fit our regression model to X and Y, and we look at the confusion matrices. And you can see that the elements in this yellow diagonal are the classification rates in which our actual in which our classifier labeled this number of values 0, and they were actually 0. This is the rate at which our classifier was able to predict ones, and they were actually ones, and this is for twos. And we can see these misclassification rates outside this diagonal, which represent for the misclassification rate for each class. So the sum is the misclassification rate for the class 0. The sum of these two is the misclassification rate for the label 1, and the sum of 12 and 19 is the misclassification rate for the class 2. And And we look at the classification report. We see that we have almost everywhere we have 0.90, like 6 as a precision and recall score, and the F score is 0.96 for some classes. For class 2, we have 0.97, and we try to get the AUCs of the ROC curve and the precision recall curve in here. They see that we have adequately high AUCs of the ROC curve, and we have 0.94, 0.95, and 96 as the AUCs in the precision recall curve. We can say that the model performs based on this information. The model, I think, is a good one because 0.94 and 0. For example, 96, they're not so low values of the AUCs. And while we're plotting here the AUCs, we see that we have a pretty sharp curve in here, and also we have corresponding PR curve representing the trade-off between precision and recall for each class on the right side. So, so as you noticed, a difference from binary classification example was that we added one more precision recall curve for the class 2. We have in here 3 by 3 matrix of the confusion, whereas in binary we had 2 over 2, and we have one row added in here in our classification report that corresponds to the report of class 2. And we in here actually in everywhere actually we perform a classification using different methods, the LDA, QDA, and the KNN, and you can review this file later on in detail, but I can tell that the all models provide pretty similar results in here. We have 20, like 35 as a misclassification rate for the label 0. We have 22, and we have 31 as misclassification rates for 1 and 2, and these are all the same as we had during logistic regression, and you later on will learn that the ROC curve and PR curves are pretty similar, and you will learn that the QDA also provides pretty similar results, and the ROC curves are quite similar, and you will learn that KNN also provides pretty similar confusion matrix scores, and the precision recall scores pretty close. And in here, the KNN, the only difference is that, let me show in here. The only difference is that for the logistic LDA and QDA, we have pretty similar ROC curves of the false positive and true positive rays, and we have a quite not so sharp curve on the corner for the KNN ROC curve, and we can also compare the PR curves in here and see that the AUC of the PR curve of A and then obviously should be lower than in these other cases. And the idea in here for each model from the binary classification is similar, and the answer to the question why did we get so similar results for each individual classifier in this example is that uh, probably uh, probably our data was let me scroll back. Probably our data that we generated in here uh, uh, was quite somehow suitable equally for each model. So each model performed like scored pretty similar performance results on these randomly generated data set. Maybe if we, for example, if we change the number of clusters or even the random state, we might not see so close results or performances of classifiers. And I mean, everything is connected with what type of data you generate, and I mean, not every time generate, but what type of data you have as an input and the quality of the data. And make sure you know how to, you already know the make classification, make sure you know how to generate a random classification dataset using the other method from the scholar datasets, that is make blobs. Make blobs, and let me show the make blobs documentation in here. It takes number of samples as an argument. It takes number of features as it did in the during the make classification, and it takes centers. There is a number of centers of the cluster location, and it takes some standard deviation parameters for our data to be generated, and it says some of other parameters also, the random state, etc. And it provides an Gaussian blobs for clustering. I mean, in here for classification, but it provides this kind of data sets in here. So this is another really good way to generate a random classification data set. And to play with that, you can use this notebook and just change the XY in the above, and from the notebook and see the performance of the classifiers using different input data sets generated. I guess that's all. And I guess if you understand what's happening in those two notebooks, you will not have difficulties in your midterm. So I guess that's all. If you have any questions.
There is one question. You said something about like splitting the training and testing sets. I missed that part. What we should be able to do there?
I mean, in here, for example, we generate X and Y, and we, for example, let's take the example of QDA. We have X and Y, and we fit our model on our X and Y. And we then get a confusion matrix, the classification report, the ROC curve, precision recall curves, AUCs, etc. for that X. And actually, another approach, a better approach, is to split the data set into the training and testing set initially. So you you might be asked to like split this X into train and test. For example, the way it is done in here for the k-fold cross-validation, and perform the steps on the test data. So in here we have X and Y, and we split the X and Y in here for the k-fold cross-validation. The idea is to have X and Y, and first separate the X and Y into training and testing sets, and then apply train test split for the k-fold cross-validation on the testing set. And at the end, you will have a model that is trained on the X train that you have split it initially, and you will be also be checking the performance of the classifier on the test data that it has never seen.
Okay. So we're doing the same thing that we're doing here, just from the start.
Yes, yeah, actually, I haven't split it the X and Y in here, but you might be asked to apply the classifiers on X train set and like evaluate this C parameter. I mean the QDA, LDA, the optimal value of K on the train set of X, and then perform, for example, the same thing on the test set. Not the same thing, I mean already built in the optimal model on the test set, and see what are the results.
Okay, thanks.
Other questions? So if not, then this notebook is on Moodle, and I wish you good luck.
Thanks.
Mekel Arpin Arpin կարամնա մեկ միատ նայենք իրա բանը, խնդիրը վրա։
Okay, հաջողություն։
Հաջողություն։